Let's continue our discussion on magnetism by talking about the magnetic force. So the magnetic force on a moving charge is what we are concerned with. And we're going to go ahead and talk about the Lorentz force. Now the Lorentz force is the magnetic force F on a charge Q that's moving at some speed V in a magnetic field of strength B. And so this is given by this equation here. F is equal to QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. Okay, so we need to also note that the SI unit for magnetic field strength, B, is called Tesla. Not Tesla the company, Tesla after the inventor Nikola Tesla. And another unit that we sometimes use is a Gauss, and 1 Gauss is equal to 10 to the negative 4th Teslas. Okay, so again, here are the units. I should have put brackets around this just to kind of break it down. So 1 Tesla is equal to 1 Newton divided by coulombs, meters per second, or is equal to 1 Newton divided by ampere times meters. Okay, remember that amperes is coulombs per second. Okay, and one more note, just to kind of give you guys an idea, the strongest permanent magnets have fields about 2 Teslas, and superconducting electromagnets can attain 10 or more Tesla. Okay. All right, so like I was saying before, there's something called the right-hand rule, and this helps us determine the direction of the electromagnetic force. So the electromagnetic force is perpendicular to the plane that is formed by the velocity vector and the magnetic field vector. So remember that vectors have direction and magnitude, so does the force. Okay, so if we have our right hand out, and this is going to be a little bit difficult to show you guys on camera, but hopefully in person it would work a lot better. So the right hand rule, we have our right hand and we point our thumb in the direction of the velocity. So in this case here, we are pointing our thumb in the direction of our velocity there. And our fingers will point in the direction of the magnetic field, B. So that would be in this direction. Okay, so we'll have our fingers and our thumb like that. And the palm of our hand, the perpendicular direction to the palm of our hand, which would be like our plane, will be the direction of our force. So our magnetic force will point, in this direction above our hand. And this is for a positive moving charge. So for a positive moving charge, note that the direction will be above your hand. So the palm of your hand and above. Okay, so up, I guess you could say. And when we have a negative charge, it's going to be the opposite. So it's going to be going down into your hand, through your hand. Okay, so that is a way that we figure out the direction of the magnetic force. And there are a couple of depictions as well. So if we don't have where we can really draw the force, sometimes we have something that's into or out of the page. So if we say something is into the page or screen, into page, we'll have something like this as our symbol in our drawing. If we have something out of the page, we will have something that looks like that. The difference is that if you have some sort of like an arrow, like a bow and arrow, we draw it. I can just draw it really quick. We have something like this, and it has like the feathers or whatever, right? So into the page, we'll be left with this to look at, right? So it'll leave us with some sort of X looking thing. If we say out of the page, the arrow will be coming towards us, and so we'll just get like the little tip coming towards us. So that's where these symbols come from. Not super important, but just to note, this would be into and then out of the page. Okay. So let's look at an example and remind us of these rules. Or this rule. So it states calculate the force on a 20 nanocoulomb positively charged, so remember that says positively charged rod, due to Earth's magnetic field if you throw it with a horizontal velocity of 10 meters per second due west, where Earth's magnetic field is due north. Okay, so the magnetic field due to Earth is equal to 5 times 10 to the negative fifth Teslas. Okay, so remember that force is equal to, let's go back, QVB sine theta. QVB sine theta. Okay. And in this case, we know that the velocity is going west, so exactly west, and our magnetic field is north. So this would give us a 90-degree angle between the velocity and the magnetic field. So theta is going to be 90 degrees. Okay, so we'll have F is equal to Q, which is 20 nanocoulombs, so that would be times 10 to the negative 9 coulombs, and the velocity 10 meters per second. The B field is 5 times 10 to the negative fifth, Tesla, sine of 90 degrees. So sine of 90 degrees is equal to 1. Okay, so I'm not real worried about that. Let me get my calculator here. Okay. So we have 20 times 10, actually 10 to, nope, hold on, 10, no, hold on, 20 times 10 to the negative 9 times 10 times 5 times 10 to the negative fifth. Okay, I think I messed that up. So let me just do that really quickly by hand. So 20 times 10 times 5 is 1,000. And then we have times 10 to the negative ninth times 10 to the negative fifth, 10 to the negative 14th if we add them, right? And then this would tell us, this is actually 10 to the third. So we'd have 1 times 10 to the negative 11th. And this is in newtons. That's because of the Tesla. Remember that Tesla is equal to, let me go back, 1 Newton, per cm over s. So Newton per c meters per second. Okay, so this is now our force here. Okay. All right, and again, due to our right-hand rule, we can see what direction our force is going, putting our thumb in the direction of the velocity and the magnetic field, we'll put our fingers in that direction, and so we'll have a magnetic force that is going down. So that would be the X there. Okay. All right. So let's move on to force it on a moving charge in a magnetic field examples. So a major example would of course be Earth. So I did discuss this a little bit before, but um, the what this represents is the um, energetic electrons and protons that are coming from cosmic rays, so like the sun or deep space, other nearby objects um, that will have some sort of cosmic rays, and they get caught in these loops of the magnetic field. So this here, right, is the B field or the magnetic field. And these are electrons and protons that are getting like kind of trapped in these magnetic field lines. And with that, they have names that they come up with, or sorry, scientists have come up with to describe those like buildup of charges, and that would be the outer Van Allen belt and the inner Van Allen belt. Again, these are the magnetic field here. So the main idea that I want you guys to take away from this is that we have some sort of energetic electrons and protons that are coming from elsewhere in the solar system and the universe and are coming and getting caught on our magnetic field. Okay. So again, kind of like shielding us. The magnetic field is shielding us from those rays. So I have a few examples of different magnetic field sources down here. Of course, we have the Earth and a bar magnet. We've looked at those. We have current in a wire. So we have current going this way. And then the B field is the blue here, going around that wire. We have a loop of wires. So we have current flowing in this way and then going around this loop here. Okay, so that's the current, and then we have a B field that's created due to that current. We also have something called a solenoid, and that is a lot of loops of wire, maybe not a lot, but more than just one loop, and this will again have current flowing through it, and it will create a magnetic field. And it looks very similar to a bar magnet, as you can tell here. Okay. All right. I'm just gonna erase a couple of things here, and then we will move on. Whoops. How far did I go? Okay. So I need to give you guys a bit of an idea about the Hall effect, and we have seen this with electricity a little bit, but this kind of puts it all into place. So we have two different occurrences of this. So one is when we have electrons that are carrying some sort of current. Okay, so we have a current that's flowing, and so the electron is moving to the in the opposite direction of the current. And then we have when we have a positive charge that moves with the current and carries the current and moves to the right. So it'll go in the same direction. So these are opposite directions and these are the same directions, okay? The electrons will feel some magnetic force towards one side of the conductor. Sorry about that. Okay. Um, the electrons will feel magnetic force toward one side of the conductor, which leaves a positive charge on the other side. So, we'll have some sort of magnetic force here that is pointing towards the one side of the conductor. So this, I forgot to mention, is a conductor. And remember, with conductors, it stores charges. Um, and so we have negative charges on this side, positive on this side. So the force, the magnetic force, is going to be toward one side, go towards one side of the conductor. And so we will have a net positive charge on this side of the conductor. And so this will leave some sort of voltage here, okay? And this voltage is called Hall EMF. And so we've seen something very similar to this in our discussion of conductors with electric fields, okay? And we'll have something very similar over here. We have a positive charge, and it'll have a buildup of the positive charges on one side of the conductor, and therefore get some Hall EMF. And note the sign. So for a positive, this is a positive charge, negative charge, oops, negative charge. We have a different sign for the EMF. So for the negative charge, we'll have a positive EMF. For a positive charge, we'll have a negative EMF. Okay. This creation of voltage is called the Hall effect. And so this Hall effect, again, is that creation of voltage across a conductor by some magnetic field. Okay. So the main idea with this is that the Hall EMF produces some electric force that balances the magnetic force on the moving charges. So everything should be in balance, okay, or in equilibrium. And the magnetic force produces charge separation, like we said, and it builds up until this equilibrium is reached. Okay, so we will have a buildup of these charges on either side of the conductor until we have an equilibrium in the system. Okay, Hall EMF can be found with this equation here. Epsilon is equal to BLV, where those are all perpendicular to each other, and the units are volts since it is a voltage. In terms of actually having to calculate this, I'm not going to ask you to. I may just ask you some very basic ideas about this. So maybe asking about, let's see. I'm trying to think of a good example of what I would maybe ask you on any kind of homework about this. Probably just some idea of what the Hall effect is. So remembering that it's some creation of voltage due to a magnetic field through a conductor. Okay, so basically understand this portion here and that separation of charge. So this separation of charge that creates some voltage called the Hall EMF. Okay, so those are the two main points that I want you guys to understand about this Hall effect. All right, so I'm going to go ahead and continue our discussion here with magnetic force on a current carrying conductor, so what we were just talking about. But in this case, we have magnetic force on some length of wire, L, carrying a current I, and a uniform magnetic field, B. So this is the depiction here. We have current going in this direction along this wire, and a magnetic field going from this north and south magnet here with some length L, which is the length of the wire um, here, and then a force here. So we have our right-hand rule yet again, and we can see it here as well, showing that we have the current is going to be in our thumb direction. Now, our fingers will still go into the magnetic field direction, and our force will be perpendicular to both of those, okay, or in the palm of our hand, okay? So let's see. And then we have our force is in newtons, okay? And in this case, we can, I just kind of broke it down. So I is in amperes, L as in meters, B is in Teslas. And so combining all of those gives you a Newton. Okay, so that magnetic force F is equal to the current times L times B sine theta. Of course, theta is again the angle between the current and the magnetic field directions. Okay. So looking at this image again, we can find the force on the wire. So let's see, force is equal to ILB sine theta. And theta in this case is a right angle. So again, this is going to be sine of 90, which equals 1. Okay, so they are perpendicular. So F is going to equal 20 amps, times L, which is 0.05 meters, right? If we convert that to meters, and then B is 1.5 Teslas. All right, so let me do that in my calculator. 20 times 0.05 times 1.5. So this equals 1.5 newtons. So this is the magnetic force on the wire. Okay, so here is our wire here. Okay. Okay, I'm going to stop here and then we will continue our discussion with torque.